Ethan, you there?
Yep. Hello.
Hi. You're the only one in here right now, and I just wanted to say that I really appreciated your participating. This class has been extremely hard for me because if you've noticed on occasion, I get dead silence out there. So I wanted to take this time to thank you for piping in when you did, okay?
Uh,
You have any questions?
I, well, I guess I had some questions on the kind of like the recent quiz.
Okay.
Just, it was kind of, I guess you said it would be like hard, but yeah, I was definitely like confused.
Okay, I will. I can't figure out why my. Okay, that's better. All right. Nope, I don't want to do that. Just let me get organized in this for a second, okay?
Yeah, okay.
Oh, there we go. Okay, good enough. Okay, I think we did this and this. Yeah, that's where we were. Okay. All right, I'm going to stop the share. Right now I got, hi all. Okay. I'm going to go back to, that's not what I want. This is what I want. All right. What specific questions were they, Ethan?
Well, I guess actually, I'm not sure if I should wait for more people since a lot of people probably were confused about this one, but like the last question, like with the fill in the blank, like I didn't really even like.
Okay. Okay, this was quiz 12.
Wait, this is quiz
13, 14,
15.
15. Okay. All right. Edit. And you said question number 10. Okay. Okay. All right. We're going to go through this today, but I was hoping you would have read forward, okay? Basically,
yeah.
Iodine undergoes beta degradation, okay? Which means that it loses an electron. A neutron gets converted into a proton, okay?
Okay.
So basically, what we do here is you have I-131 going to xenon-131 plus a electron, right? Does that make sense to you, Ethan?
Wait, so that's, yeah, I guess that like undergoes beta degradation.
Yes, it loses an electron, okay? Now, when something like this happens, energy gets released because you have less mass in the products than you started with the reactants. Okay, Ethan?
Oh, so you have less, okay, yeah, like less products, okay.
Morning. So what you're doing is you're taking 130.9061246 and you're subtracting the products from that, which is 130.905084113. And you also have to add the mass of the electron in there because this is a case where the mass of the electron does matter. So you subtract out that as well. And what that is that's something called the mass defect. That's in AMUs. You then have to multiply the AMUs by 1.66 times 10, I think it's to the minus 27th kilograms per AMU. This gives you kilograms. Now, once you have the kilograms, you multiply that by C squared to get the energy. Okay?
Okay.
Are you with me? Are you with me so far, Ethan?
Get. Okay, so wait. So just to kind of make sure I'm following. So you take the mass of like I-131 and subtract it, like
subtract out the xenon,
and the electron mass.
That will give you a very, very, very small number.
Okay. And then you multiply that.
You multiply it by 1.66 times 1.66054 times 10 to the minus 7th kilograms per AMU.
And to convert it to kilograms,
you need to have kilograms.
Yep.
Because a joule is a kilogram meter square per second square. That is what a joule is.
Then you multiply that by.
You multiply the kilograms by the speed of light squared.
Okay.
E equals mc squared. But that is the energy for one atom. Okay? What you have to do is you have to multiply that by Avogadro's number to get the amount of energy per mole. Then you have to convert the 200 grams of iodine into moles and multiply that by the kilojoules per mole.
Okay, so wait, you convert the iodine to
Okay, let's go ahead and do this, okay? All right. I-131 converts into xenon 131 plus a beta particle. Okay, the beta particle is an electron. So to get the mass defect is products minus reactants. Okay, so this means I got to take 130.9050, and don't get lazy, guys, 8413. I'm sorry, wrong. 0.906, 1246 minus 130.905, 08413 minus 0.000548, 579, 909. Okay, now I got to do this math out. 0.906, 1246 minus 130.905, 08413 minus 0.0005485 79909. I'm just going to keep this in, I better not. 4.91 89 e to the minus 4. This is AMUs. I multiply this by 1.66. Where's it at? 66054. E to the minus 27th kilojoules per AMU. And I get 8.16 803 e to the minus 31 kilojoules. I multiply this by 2.9979 e to the 8th quantity squared. And I end up with 7.30 e to the minus 14. Yes, I know I'm not dealing with the sig figs correctly, but I don't really have time to do that. This is in joules. I multiply that by 1 kilojoule per mole, or 1 kilojoule per joule. Times 1 kilojoule per 1,000 joules, and this equals 7.30 e to the minus 17th kilojoules per 1 molecule times 6.022 e to the 23rd molecules per mole, and this gives me 4.40 e to the 10th kilojoules per mole. Then I have 200 grams of iodine times 130.906 grams per mole, or divided by 1 mole divided by 130.906. This gives me 1.527 moles. I multiply that by 4.40 kilojoules per mole. And I get 6.72 e to the 10th kilojoules. You follow through, Ethan?
Yeah, I think I'm following here.
Okay. I'm going to give everybody credit for it because, for one thing, I screwed that up. So that's the one thing. And in retrospect, I didn't get as far as I wanted to. So I didn't get as far as I wanted to. So in any case, everybody's getting credit for it. It's a hard problem. Hold on 1 second, guys. Hello?
Thank you.
Sorry, it was a local number, so I thought maybe somebody was having trouble getting on here. Do I have everybody in here that's here? I got 15 people in. We're going to go through that problem. We are going to go through that problem today. This is a mass defect turned into energy. We will go through that today. It's one of the last things we're going to do. So, Jenna, did you have a comment?
I was just going to say, I think people were trying to get in, but I just looked and they're all in now, so never mind.
Yeah, I know I had 5 people hanging while I was doing the problem. So thank you very much, Jenna.
I have a question.
Benita,
Hi, this quiz is due Sunday, right?
I'm sorry?
This quiz is due on Sunday, right? Or did
In that case, then everything is good.
Okay. Okay. All right.
That's why,
get
I'm sorry.
that.
Thank you, Danita. Thank you, Benita. You're absolutely right. It is due on Sunday. So that's why it's such a hard problem. I've corrected the error and you guys have had the benefit of having it worked out. All right, Benita, did you get my email?
Yes, I did. Thank you.
Regarding, I apologize. I don't know why that got entered in as it did, but apparently I just entered the post and I don't know why it got entered in by that, but you got your grade, okay?
Thank you.
Anybody have any other questions? Ethan,
I guess,
I'm not going to answer any more questions since the quiz is still live.
yeah, okay, that's fair.
All right. If you want to, Ethan, since you've already submitted it, you can stay after class and I'll go over what you need to go over at that time. Okay.
Okay,
Fair enough.
yep.
Anybody have any other questions about what we did Tuesday regarding the calculations of electrochemistry? You are going to be responsible for knowing how to determine a standard cell. You're going to be responsible for determining a cell at non-standard conditions, determining what the Gibbs free energy is by multiplying the number of electrons transferred by the Faraday by the E of either the cell, standard or non-standard cell. And you're also going to have to be able to determine Ks. That's what we went over at the first part of class on Tuesday. Anybody have any other questions, guys?
Yeah, I do. You're gonna give us all the values for, like, as in cell potentials or
Yes.
like for
Yes.
okay.
Yes, Manuel, I will give you all those in the problem.
So we
Okay?
don't gotta look them up or
No, you
print
do
them.
not
Okay.
have to look them up or have a table. I will put them right in the problem for you. Any other questions, ladies and gentlemen? Okay, where we ended. We ended with the decays. And basically, I talked to several of you asking the question, what was going to be the fill in the blank? And the main thing you have to do with these type of problems is you have to realize that whatever is on the left side of the arrow has to be equal by the right side. So my left side has a mass number of 211. So whatever the unknown is here has to add with the beta particle to equal 211. The beta particle has no mass number, so the mass number of my unknown has to be 211. My atomic number has to be added to -1 to equal 82. My atomic mass, or my atomic number is going to be 83 then. This is how you work these type of problems. Second one down, 214 equals 210 plus what? Has to be 4. 83 equals 81 plus what? 2. So the thing that I add on with this is going to be something with the mass number of 4 and an atomic number of 2. That is going to be an alpha particle. Does anybody have any questions about decays and how we complete reactions? All right. Now, anything more than hydrogen, anything that has an atomic number more than hydrogen is going to have repulsion because the protons are in the nucleus. What has to happen is we have to have a strong nuclear force that keeps the nucleus from flying apart. Ultimately, and we will get into this later, what has to happen is we have to transfer some of the mass of the protons and neutrons in the nucleus. Some of that mass has to be converted to energy. And so that since it has to be converted to energy to keep the molecule, the nucleus together, the number, if we would add up the total number of protons with the total number of neutrons, it will never equal what the atomic weight of the atom is, what the atomic weight of the isotope is, because some of that energy is transferred over into keeping the nucleus together. The other thing is we need neutrons. If we just had protons in there, there wouldn't be enough mass lost to keep the protons together. We couldn't have enough energy to keep those two protons together. So we have to separate them by adding neutrons in there. So therefore, when we have, there's going to be a ratio of neutrons to protons. And we need a very specific ratio in order to keep the nucleus together. It's kind of a delicate balancing act we're doing here. We're adding neutrons to keep the protons separate, but the more stuff we add, the more unstable the nucleus is. So we got to keep our ratios in line. Now, up to 20, up to calcium, if you look at a periodic table, you can pretty much guess what the atomic weight is by doubling the number of protons. You can kind of guess the mass number by doubling the number of protons. This is because up to 20, the neutron to proton ratio is close to 1 to 1. Then we start to vary. As they get larger, you have more and more positive charge that's in the nucleus, so you need more and more neutrons to keep them separate. Now, there is a specific ratio that gets developed between number of neutrons and number of protons. So if I'm looking at a graph, there is a certain area where you can have a little bit of difference between the number of neutrons and protons and still have a stable isotope. That particular wide area of this ratio is called the belt of stability. If you're in the belt of stability, your nucleus is stable, relatively stable, and it won't fly apart. If you have a nucleus that has too many neutrons, in other words, we are above the belt of stability. What happens is we have too many neutrons. We want to get that ratio down of neutrons to protons. The way we do that is we convert neutrons into protons. The way the decay that does that is beta decay. We understand that, ladies and gentlemen? Okay. Now, if they're below the state of, Jana, do you have a question?
Yeah, I do. You said it turns the neutrons into protons?
Yes. A beta, what happens is a neutron releases an electron. Okay, Jana? So the neutron hasn't lost any weight, but it's lost the negative positive aspect of it. So it's lost its negative character. It only has positive. So in beta decay, the neutron gets converted into a proton.
All right.
If I have a nucleus below the belt, this means that I have too many protons. If I have too many protons, then I have to convert a proton into a neutron. I can do that by one of two ways. Either by positron emission, and a positron is kind of the same thing as an electron, only what happens is it loses its positive character. So a proton that is positive loses a kind of like electron-like particle, only instead of being negatively charged, a positron is positively charged. So a proton can do that, or a proton can capture an electron. In either case, the proton gets converted to a neutron if I have too many protons. Now, basically, what you can do, you can figure this out if you look at the periodic chart. The atomic mass is just an average of the stable nuclides. And basically what this represents is a neutron to proton ratio that's just about right. So if we have iodine 128 and my atomic mass is 120, the average atomic mass is 126.9. So if the weight that I have is higher than the periodic weight, what's going to happen is you're going to have beta decay because you have too many neutrons. If the weight of the isotope is lower than the periodic table value, what's going to happen is you have electron capture or positron. You need to get more protons. Important slide here, guys. If the weight of the isotope is higher than the periodic table value, beta decay occurs. You have a neutron being converted into a proton. If the weight is lower than the periodic table value, you're either going to have electron capture or positron decay. In either case, what happens is you get a proton converted into a neutron. So I have lead 212. The normal atomic weight of lead is 207.2. Is it going to undergo positron electron capture, or is it going to undergo beta decay?
Beta decay.
It's too high. It's going to undergo beta decay. Good. Thank you. Radon 224. I'm sorry, not radon, radium. And I got to find out where it is. Radium 224. I'm comparing that to the atomic value of 226. Beta or positron?
Positron.
It's lower. It's going to be positron. Polonium 248. Its normal atomic weight is 244. Benita.
That's the positron one.
It's higher. The
Oh.
weight is higher than the atomic weight.
Oh, so it's the beta decay.
It's going to be beta decay. Polonium 206. And its normal atomic weight is 208. Ethan.
Yeah.
Polonium, polonium 206. Normal atomic weight is 208.
So let's see, point. It does not wait. So it go positive.
Second. Polonium
positron.
weighs 208. The isotope we're talking about is 204. Does it undergo positron or beta decay?
Positron.
Positron. The weight is lower than the weight of the atomic weight. Are you fairly good, guys? You been to Amsterdam, Ethan?
Yeah.
Great place, fantastic city. I got mugged there once and I still like it.
Oh.
All right, you go beyond 83. You go beyond 83. What the nuclei have a tendency to do is decay by alpha emission. But when you have these real large radioactive nuclei, they're not going to stabilize in one step. So you have a radioactive series that occurs. First thing that happens to uranium, it loses an alpha particle to make thorium. Then it gains a positron to go to palladium. Then it goes to another one to get to uranium. Then it goes back to thorium, radium, radon. And there's this whole series of steps that occurs until you get to a final stable molecule. Generally speaking, they will end up being lead. Again, generally speaking. So if I have a whole series of these reactions, it's just called a radioactive series. Some trends. Nuclei with 2, 8, 20, 28, 50, 82 protons, or 2, 8, 20, 28, 50, 82, or 126 neutrons tend to be more stable than nuclei with a different number. Don't write it down. Don't write this down. The chart is what you need to see. If you have an even number of protons and an even number of neutrons, you have a whole lot of stable isotopes. Even protons, odd neutrons, you have a decent amount. Odd protons, even neutrons, you have a decent amount. But when you have an odd number of protons and an odd number of neutrons, you have very, very few stable isotopes. Again, this is more of a general knowledge thing. I'm not going to ask you a question on it. Kinetics of radioactivity. It's a first order process. It's bound by the integrated rate law of the first order. It's bound by the half-life and the rate of the first order reaction. As a first order reaction, the ln of the nuclei left at some time t divided by the amount we started with is going to be equal to KT. In other words, all I'm doing is I'm taking the integrated rate law. I'm subtracting ln of A0 from both sides. ln of A minus ln of A0, mathematically, I could turn it into that term. That is equal to negative KT. If I substitute number of nucleides for the concentration of A and number of nucleides at time t for AT, I can make a new formula, And basically all I have to do is count the atoms. And the atoms are going to be equal to K, negative K times T. Half-life. If I go back to the original equation, the original chart, my half-life is equal to 0.693 divided by K. Notice, K is in both formulas. So all I have to do is divide 0.693 by K, and that's going to equal my half-life. Now, the reason I can do that, my nucleides at time t divided by the nucleides at nt is equal to 1/2 n0. So if I substitute 1/2 n0 in there and take the ln of that, that's going to be a negative number divided by a negative k. So my half-life is 0.693 divided by k. So what we can do is we can determine the amount of a radioactive nuclide at some time. And ultimately, what we're going to be able is to determine the age of that object. The radioactive decay of thallium-206 to lead-206 has a half-life of 4.20 minutes. If I start with that many atoms, calculate the number left after 42 minutes. Strategy. I know what the half-life is. I'm going to take the half-life, divide it into 0.693, and I will get the value of K. If I know what K is, and I know how many I started with and how much time it took, I can multiply K by the time, raise it to e to that power, and multiply it by the amount I started with. I will have the amount I have left. That's the strategy we're going to do here. So the first step, I'm going to find out what my K is. I'm going to take 0.693 and divide it by my half-life. That gives me the value of my rate constant. I have my rate constant. I'm going to multiply that by the time. That's going to give me 6.93. 6.93 is equal to the ln of the nucleides left divided by the nucleides I started with. To get rid of the ln, I have to raise negative 6.93 to e to that power. That number is 9.78 times 10 to the minus 4th. I multiply that by 5 times 10 to the 22nd, and I have the amount of nucleides left. Any questions, ladies and gentlemen?
I do. So we're
Daniel,
obviously we're solving for NT, correct?
yes.
Okay. And you got the negative 0.165 because you plugged in the 165 from the
No,
half-life reaction.
The half-life equation is the half-life is equal to 0.693 divided by the rate constant. So if that's true, then the rate constant is equal to 0.693 divided by the half-life.
Okay.
We good?
Gotcha. Yeah, could you go to like the next slide where you did all the steps?
Okay, the K value I just figured out, right? My initial
Okay.
problem gave me the time. My initial problem gave me the time, the half-life, and the number of particles I had originally. So I simply take my K value, which I figured out from the half-life, multiply that by the time, and I ended up getting a negative 6.93. As a side note, ladies and gentlemen, you have to realize the time that your half-life is. So my K value is actually, my K value should be in 0.165 minutes to the minus 1. And let me go fix that right now. The reason that's important is that I need, if I give you a time that's in something other than minutes, then I'm going to have to convert that to whatever time my K was originally determined in. Any other questions about this problem, guys?
Can you please do another one?
Certainly. Is this
Thank
kind
you.
of like, thank you, sir, may I have another? Are you Kevin Bacon bending over in Animal House? That's where that expression came from. If you didn't know, in Animal House, Kevin Bacon's applying to be a frat at a very sadistic fraternity, and they paddle him. Okay. Calculate the time required for 95% of a sample to decay. And I give you the half-life. Note, in the first question, I was asking you how many nuclei were left. In this equation, I'm solving for time. And there is a trick here. First of all, I'm going to find K from the half-life, just like I did before. And then I'm going to use K and the ratio of the sample to determine T. But there is a trick. When I give you this expression, log of NT over N0, is that the amount of nucleides left, or is that the amount converted?
That's the total, correct? It's not the 90% that
No,
you're asking.
that's the amount at time T. That's what the NT stands for, not total, the N left at time T. So Manuel, is it the amount of nucleides left, or is it the amount of nucleides that reacted?
That reacted? Or
NT, the amount at time T. That's the amount of nucleides left at time
Left.
T. Does that make sense, Manuel?
yes. Mhm.
So if 95% decayed, how many are left?
5%.
5%. Again, it's a trick of this particular question. So again, first step, I'm going to take my half-life. Remember, that's in years. I'm going to take my half-life and use that to find K. I'm going to take 0.693. I'm going to divide it by 6580 years. That's going to give me my K value of 105 times 10 to the minus 1, or 10 to the minus 4 years to the minus 1. Going to plug K into that equation. So I'm going to have the ln of 5 over 100. 5 divided by 100 is 0.05. The ln of that number times 105 times 10 to the minus 4th. I'm sorry, divided by 1.5 times 10 to the minus 4th gives me 28,500 years.
I'm sorry. Could you go back to the previous slide? I'm sorry.
Be happy to. Half-life is 6580, Manuel.
Okay.
So
Thank
I'm
you.
dividing 0.693 by 6580, and I get 1.05 times 10 to the minus fourth. Since negative KT is equal to ln of A over A0, I divide both sides by negative KT. The negative sign goes away. So I have the ln of 0.0500 times 1.05 times 10 to the minus fourth. This gives me 28,500 years. Is this a reasonable number? Let's think about it. If I have one half-life, how many particles, what's the percentage of particles I have left?
Is it 50%?
50%. Okay, Parker, I go 2 half-lives. How many are left?
25%?
3 half-lives?
Oh, geez. 12.5%?
Okay, now 4 half-lives.
Oh, geez. 6.25%.
Okay, is that around 95% approximately?
Yes.
Okay, now I've said 4 half-lives, right? I divide 6580 into 28,500. Isn't that about 4? 4 plus
Yeah.
change. So is this a reasonable number?
Yes.
Calculate the time required for 90% to remain. Again, this now is a change of the wording on the problem. 95% haven't decayed. I have 95% left. So my ratio of A to A0 is going to be 0.95 rather than 0.05. And it works out to be a whole lot less time. Questions, ladies and gentlemen?
Yeah, I have a question. Earlier you had in the equation of negative KT equals ln or whatever, it you guys started off with it being negative.
Yeah.
Could you explain why it's negative in this case? Not the
Why?
negative KT.
Okay.
Yeah, isn't it normally first order the ln of?
I screwed up. I screwed up because I was trying to think while I was teaching. I always get in trouble when I try and think while I was teaching. Okay. All right. The ln of any number below 1. The ln of 1 is 0. If you have a number less than 1, a fraction, that number is going to be negative.
Okay.
So I have a
that's
negative
why.
times a negative. My answer ends up being positive. Thank you for catching that, Manuel. That is the reason that the number of years is going to be positive. Any other questions, ladies and gentlemen? So, if I have the rate law, my rate is going to be equal to K times my original concentration. So, if I start off, my rate is going to be equal to my rate constant times the number of nuclides when I start. But remember, as I get less and less number, my rate is going to decrease. So that my rate at time t is going to be equal to my rate constant times the number of particles I have left at time t. You're scratching your neck, Manuel, and you are You're scratching your neck and you are,
Confused.
guys, I'm not seeing any faces. Visualize. The only face I'm seeing is Manuel's. Visualize. I am only counting those people present that visualize now. Manuel.
Professor,
Yes, Ether.
I can't open my camera because my Wi-Fi is not really good here.
Do the best you can.
Professor,
Yes.
I'm getting my braces taken off right now, so I can't really like show the
Why,
camera.
Anaya, why did you set up an appointment during class time?
I'm sorry.
Nothing. 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 Don't worry about it.
Okay.
Guys, I want to see your faces.
You can see me, right?
Yeah, I can see you, Benita. Thank you very much.
Yeah, just making sure you can see me.
All right, we're good. We're good. All right, ladies and gentlemen, do you understand that if I determine from the half-life what K is, and I know what my number of nucleides are, I can determine the rate by simply taking the rate constant times the number of nucleides left, because it decreases as time goes on. I can also, because of this factor, if I divide my rate at times t by my rate at times 0, I can convert that. My rate is going to be, my k's cancel, and then what happens is I substitute this into my original equation, and I get the ln of rate t over rate 0 is now equal to a minus kt. Now, if necessary, I can relate rates to time. Now, let's get into carbon dating. Ethan, do you breathe after you die?
No.
Nope. So when you are breathing, you are exhaling carbon dioxide, correct?
Mhm.
So what you are doing is you're taking in normal carbon and you're exhaling carbon dioxide, correct?
Correct.
And you've agreed that when you die, you no longer do that, correct?
Yep.
So when you die, are you consuming food?
No.
And you are not exhaling anymore, right?
You're not.
So you are not replacing the carbon. Is that correct?
That is correct.
So if I have a radioactive isotope of carbon and I'm dead, I'm not replacing it. So my carbon that is radioactive is decaying at the half-life of that radioactive species. This is the basis for radioactive decay. I'm comparing the carbon-14 activity to what it should have been originally. I measured the disintegrations of carbon-14 at 11.6 disintegrations per second. Basically, I've got a Geiger counter. If I have carbon of equal mass from fresh wood, I get 16.2 disintegrations per second. What that means is that I have used up in my dead wood, I have used up some of my carbon-14. It's not as active as fresh wood. The half-life of carbon-14 is 15 years. What is the age of my sample? Again, I have ln nt over N0. This is a rate. My disintegrations per second is a rate versus my disintegrations per time at fresh wood. This is equal to a negative KT. I have my half-life. I can determine what K is and plug it into that equation and get my time. First step. And guys, you might as well just write this number down somewhere because you're going to need it in the future. If I divide 0.693 by the half-life of carbon, I get 1.21 times 10 to the minus 4 years to the minus 1. That's what K is. I then take the ln of my rate at time t over rate at time 0, put that equal to negative 1.21 times 10 to the minus 4th years to the minus 1 times t. I take the ln of 0.716, divide that by 1.21 times 10 to the minus 4th. I get 2,760 years. Any questions? This is how they determine the age of antiquity objects. Any questions, guys? Same problem we've been working earlier. The age of some animal bones was determined by carbon-14 dating to be 8.4 times 10 to the 3rd years old. Calculate the activity of the carbon-14 in the bones in disintegrations per minute, given that the original activity was 15.3. I don't have to determine, or actually I do have to determine K. Again, K is equal to 1.21 times 10 to the minus 4th. I multiply that by the years, raise e to that power, then multiply it by my original disintegrations per minute. This gives me that my rate at time t is now 5.52 disintegrations a minute. Again, I will open it to the floor. Any questions? All you're doing is manipulating basically two equations to determine various things. Any questions before I get into boom? Any questions?
No.
All right. Now, there is a tremendous amount of energy that is stored in every nucleus. This is way back in the early 20s, 1920s, when they started to look into this. They discovered that by using Einstein's equation, they knew that the nucleus was losing weight. If the nucleus is losing weight, then it is going to evolve a whole bunch of energy. So we're going to be able to use, finally, you're going to be able to use Einstein's equation. Basically, if we're dealing with normal chemical equations, if I look at the mass that gets converted, it's minimal in comparison to what is happening with other parts of the system. However, basically, if I'm considering the energy that is lost in comparison in a nuclear reactor, it gets to be much, much higher. So in dealing with this, we have to use a new term. The new term we're going to use is called AMU, or atomic mass unit. And an AMU is defined as being 1/12 the mass of a carbon-12 atom. Effectively, it's the weight of a proton or a neutron, the average of a proton or neutron. And so 1 AMU is equal to 1.66 times 10 to the minus 27 kilograms. Important slide. You need to know what an AMU unit is and what the conversion rate is. Now, nuclear reactions occur with a loss of mass. The mass that's lost is known as the mass defect. And I can use that mass defect in the E is equal to MC squared. Put that in, if it's in kilograms, multiply it by the speed of light squared. That will give me my energy in joules, because a joule is equal to a meter squared kilogram divided by a second squared. In the fission of 1 atom of uranium, 1 atom of uranium, 238 to 235, how much energy is produced? I just simply subtract the mass of the uranium I begin with to the mass that I end up with. This ends up to be 0.18489 AMUs. I multiply that by 1.66 times 10 to the minus 27th kilograms per AMU. That will give me kilograms. I multiply that number by 2.99 times 10 to the 8th squared. And I get 2.7 times 10 to the minus 11th. Ether, do you think this is a big number?
Yes.
2.7 times 10 to the minus 11. 0.000000000027 joules. Is that a whole bunch?
No.
Then why are we worried about it? Why do we care? How many molecules did I just figure out the energy change of?
Is it the 0.18?
No, that's the weight. AMUs are weight.
2.99?
Nope, that's the speed of light. How many molecules am I talking about that I have 2.7 times 10 to the minus 11 joules? What's the weight? What is the weight?
1.66?
Nope.
That's not?
I'll throw it out to somebody else. How many molecules am I talking about, guys? How many molecules am I talking about? Did I hear the answer?
One.
One. All I'm dealing with this amount of joules is 1 molecule.
I have a question.
Okay, go for it, Emily.
I'm confused as to where you pulled the 236 minus the 235.
The 236 is the weight of uranium-238. The 235 is the weight of uranium-235. Okay? Of one atom. Of 1 atom of each. Okay, Emily?
So would you give that to us?
Yes.
Or okay.
I have a question before you go on.
Yeah, Benita.
For C, is C equal to the 2.99 times 10 to the 8th?
Yes, that's the speed of light. That's the speed of light. It's a constant.
Okay, that's squared. Okay.
Okay. So if I'm dealing with 1 atom, This is the number of AMUs per atom. If I have a mole's worth, this means I have 1.85 times 10 to the minus fourth kilograms. So if I multiply that times my speed of light, I end up with a whole bunch more. So if I'm dealing with 1 mole of uranium changing, in other words, half a pound. If I'm dealing with 1 mole of uranium, half a pound of uranium, I make 1.7 times 10 to the 13th joules, or 17 trillion kilojoules for half a pound. In comparison, if I have 1 mole of HCl, mix that with 1 mole of NaOH, I get 55.7 kilojoules. If I combust 1 mole of butane, that yields 5,315 kilojoules. So we are talking an astronomical advance. Calculate the energy of the reaction of 1 mole of carbon-14 to yield 1 mole of N14 and 1 mole of beta particles. The mass of carbon-14 is 14.003241. The mass of nitrogen-14 is 14.003074. My mass defect, the amount of mass that I lost, is equal to 0.000167 AMUs. I have to turn this into kilograms. Multiply it by 1.66 times 10 to the minus 27th kilograms per AMU. I've got my mass defect of 2.7 times e to the minus 31 kilograms. Multiply that by 3 times 10 to the 8th squared. This gives me 2.48 e to the minus 14th joules per 1 molecule. If I multiply that per 1 molecule by the number of atoms in 1 mole, I get 1.49 e to the 10th joules. Questions, ladies and gentlemen? Find the energy released in kilojoules per mole during the following fusion reaction. Fusion. I'm actually taking 2 molecules, putting them together. Fusion is when you put 2 atoms together and make a bigger one. Decay is when you take an atom and make it into smaller ones. So I've got the AMUs of boron 11 and helium. I have the mass of a neutron and nitrogen 14. What's the first step, Benita, that I'm going to do here?
I have no idea.
Okay. Emily?
Is it the mass defect?
I'm going to take the mass I start with and subtract it by the mass I end up with. First step in all of these problems is going to be determining the mass defect. So I do this math out, do this subtraction out, I get negative 0.0159. The next step is to turn the AMUs to kilograms by multiplying by the conversion. Then I use E is equal to MC squared. I do that math out and I end up with 2.36 times 10 to the minus 12 joules. And since I didn't give you a weight, that's as far as you can go with this problem. Any questions, ladies and gentlemen?
So for these ones, you do reactants minus products,
Uh,
kind of.
well,
That's what you
basically,
start with.
no, in effect, Jenna, in effect, you're doing, okay. You're right, Jenna. You're right.
Okay.
You do reactants minus products because you're going to end up with a negative number. And these reactions are always exothermic.
Gotcha. Okay.
Okay. That's why you have a negative sign.
Okay. Thank you.
Okay.
Mhm.
Any other questions, ladies and gentlemen? All right. So how do we tap that energy? How do we make Hiroshima go boom?
We divide the particles
But how do we do it, Jana?
with heat and energy.
This is just, you have to understand, this is random, right? Do these just stop at the end? We have to realize, Jana, that our first reaction, when we throw that the neutron, when we throw that neutron at the uranium, it causes that uranium to break up into krypton and barium. But look what else happens. We get 3 more neutrons. We take these 3 neutrons and we put 3 more uraniums out there. The 3 neutrons hit the 3 new uraniums. Each one of those uraniums creates 3 more neutrons. So where I had 1 to begin with, if I have enough uraniums out here, I now have 9 neutrons. Then I have each one of those splits off into 3. I get 27, then 81, then 243, then 729. And beyond that, I'm not going to go. So what I'm doing is I am bombarding originally my nucleus with 1 neutron. I'm splitting that into more neutrons that get split off from the original nucleus. That in turn, each daughter then splits off 2 neutrons, which hit the granddaughter, which each split off 2 neutrons. Has anybody ever seen a movie called Pay It Forward? Great movie, phenomenal movie. Basically, this teacher gives his students a project. And the idea of the project is to do something that will better mankind. And so all these other students in this class have these real fancy, grandiose ideas of what they're going to do to make the world a better place. And this one little kid just thinks, what I'm going to do is I'm going to do 3 kind acts to 3 different people. And the only thing I want from doing these 3 kind acts from these people is they have to pay it forward. They have to do kind acts for 3 people each. And it multiplies. And it got to be a phenomenon that enveloped the world to the point where it got to be a news story. I will not spoil the movie for you by telling you the ending. But that is the same thing. Don't give me a frown, Jenna.
I know the end of the movie.
It's a sad movie.
It's a sad movie.
So
What's the ending?
I'm not going to tell you. It's like, Manuel, there's another movie called Single White Female, in which this crazy person is living with this crazy female is living with another female. And in the middle of the movie, the crazy female gave the other one a puppy. I looked at my wife and I said, does anything happen to the puppy? You notice I didn't ask if anything happened to the person. I asked if anything happened to the puppy. And my wife lied. I have not, I saw this movie 10 years ago. I have not forgiven her yet. So, Manuel, I am not going to spoil the movie for you. It is worth watching. If you read the book, it's also fantastic. So what happens is I get all of these radionuclides going. If I don't have enough material, if I don't have enough fissile material there, then my reaction's going to die off. But if I do have enough, the amount present that needs to be present for a chain reaction to be sustained is called critical mass. So you have to have a certain amount of the material present in order to get the chain reaction to sustain. That is called the critical mass. And by the way, when I'm creating more neutrons in the daughter ions and more in the granddaughter ions, that is called a nuclear chain reaction. Now, what happens in a reactor? Basically, we're creating a whole bunch of energy. So we have, I'm going to make this bigger. So what happens is we have a reactor. And in the reactor, I've got neutrons flying at uranium. So I'm getting a whole bunch of energy created. This energy is this particular reactor is surrounded by water. So I'm creating super hot water that goes through and creates steam. That steam reacts with the turbine, generating electricity. And then that steam, after it hits the turbine, condenses back to water and it's pumped back. Now, you don't want the water. You don't want the water that is in the that's around the reactor to be exposed to the water that's going through the turbine, because that has been contaminated with radioactivity. So basically, you get this water, it gets pumped back through, and some of it goes into the river, some of it gets pumped back through to the water being circulated. And that is why there are no fish around nuclear reactors. Now, it is kept in check by the use of control rods. The control rods are graphite rods. And what the graphite rods do is they interrupt the flow of the neutrons from reaching the uranium fuel rods. The main trouble with nuclear energy is the fact that we are generating tons and tons of this material that is no longer usable in nuclear reactors, and yet it takes thousands upon thousands of years for this to go away, for it to be rendered safe again. And basically what they do with this material is they either store it in caves deep below the ground, or they store it in above ground sites. Each of them have their own advantages. The above ground sites being, you can see if something's gone wrong. If it's down miles below the earth, you can't tell what's gone wrong, so you don't know. A solution to this: fusion has more power than fission. When we're dealing with uranium decay, that's fission, breaking up the molecule. Fusion is actually taking two molecules, pushing them together, putting two hydrogens together to make helium. The great news, it's not the materials that are left over. As a matter of fact, helium is a great byproduct. There's not enough helium in the world. So that would be a great byproduct. The bad news is that in order to do this, in order to initiate the reaction, you need several million kelvins of energy. And they have worked out a magnetic device that they're looking into to solving this particular problem. Now, when I add 2 protons and 2 neutrons, when I add that mass up and compare it to the mass of a helium, I don't have as much mass in the helium as I do in the protons and neutrons. This is where it gets into the energy needed to keep the nucleus together. So I have a mass defect. When I make that helium, I lose 0.03038 atomic mass units. This is known as this can be converted to energy, and the energy that it converts to is known as the nuclear binding energy. So I take the mass defect and I multiply it by the kilograms, and I multiply that by the speed of light squared. This is the nuclear binding energy to keep a helium nucleus together. Now, for whatever reason, they don't like joules. They want something that is a little more manageable. So they developed a new term called an MeV. And 1 MeV is equal to 1.602 times 10 to the negative 13 joules. So if I take the amount of joules needed to keep the helium together and divide it by, or multiply it by 1 MeV over 1.602 times 10 to the 13th joules, this gives me 28.17 MeVs. Now, I've got a similar problem. Okay, I can solve this and do it in a direct conversion. The direct conversion is 1 AMU is equal to 931.5 MeVs. So if I take the mass defect, multiply it by 931.5, I get a similar result. The differences are due to rounding. You have to understand that things are getting rounded, and the more you round, the more your final answers are going to be off. If I want to compare one nucleus to the other in terms of the energy, I have to divide it by the nucleons, the number of neutrons plus protons. For helium, this is 4. So I take the nuclear binding energy for the helium nucleus, divide that by 4, and I get 7.075 MeVs per nucleon. What is the mass defect and the nuclear binding energy for copper-63? Weight of copper-63 is 62.91367 AMUs. I have 29 protons So this means I have 34 neutrons. My proton mass, I'm going to take my number of protons times the mass of a proton. This gives me 29.22852 AMUs. Neutrons, number of neutrons times the mass of a neutron. Note, they're a little bit different. That adds up to 34.29478. So the total AMUs for 29 protons and 34 neutrons is 63.52330. My carbon weighed 62.91367. So this ends up being a mass defect of 0.609963. I multiply it by 931.5 MEVs per AMU. I've got 567.9 MEVs. But this is for 63 particles. So to get the energy per nucleon, I divide that by my 63, and I get a binding energy of 9.014 MEVs per nucleon.
Can you go back 2 slides really quick?
2 slides? Certainly, Jenna. Is this the slide you wanted?
No, the one right before it.
That one?
Yes, thank you. I just needed to get down the rest of the numbers. Okay, I'm good. Thank you.
Any other questions, ladies and gentlemen?
Oh yeah, I'm sorry. I'm trying to figure out where the 62 came from again.
Where the what?
From adding.
Okay,
You got the 62
in the
from
original
adding-
problem.
Okay.
Manual?
Mm-hmm.
Sorry. This is the original problem.
Okay.
The weight of the weight of copper 63 is 62.91367. You have to understand, if I weigh the individual protons and I weigh the individual neutrons and add them together, I'm going to have more weight than the carbon 63 has. That's because some of the weight from the protons and neutrons has been used to keep the nucleus of the copper 63 together.
Okay.
Does that make sense, Manuel?
Yeah. You said like a second ago carbon, that there's no carbon in this problem.
Copper, no carbon, copper.
Okay. So you take the 62.91367 and you.
Well, what I'm going to first do, Manuel, I've got 29 protons. I know that my mass number is 63, so I'm going to subtract protons from my mass number to get the number of neutrons. Then what I'm going to do is I'm going to take my protons, multiply it by the weight of each proton. This gives me the mass of all the protons. I'm going to take the neutrons, multiply it by the mass of a neutron. This gives me the weight of all the neutrons. I add them together, and that will give me the total weight of all the protons and neutrons. Now what I'm going to do is I'm going to subtract out the weight of my carbon 63. That difference is the mass of copper. Did I just say carbon again?
Yeah, you like carbon.
Apparently I do. I'm going to subtract out the weight of copper 63. That gives me a mass defect of 0.60963. I could solve the problem by converting this to kilograms and then multiplying kilograms by the speed of light. That would give me joules, and I can convert joules to AMUs. Or joules, yeah. I can convert joules to MEVs that way. Or I can just do the straight conversion. One AMU is equal to 931.5 MEVs. So I multiply the AMUs by this, I get the MEVs directly. but that's for 63 nucleons. In order to get the binding energy per nucleon, I have to divide this by all the nucleons, which is 63. So I get 9.014 MeVs per nucleon.
Gotcha. Thank you.
Any other questions?
Yes, I have a quick question.
I'm here.
So for the proton mass and the neutron mass, like the 1.00788.
That would be given to you.
Oh, okay. Okay, that was my question.
You don't have to memorize it.
Okay.
Okay? I believe this is the last problem of the semester, guys. Just like we did for the carbon copper. Just like we did for the copper. We know that iodine has 53 protons. If it's iodine 126, then I subtracted 53 from the 126, I get 73 neutrons. I multiply my protons by the weight of a proton, I get 53.4176. I multiply my neutrons by the weight of a neutron, I get 73.6329. I add both of them together, I get 127.0505. I need the mass defect. Iodine 126 weighs this. This is the weight of the protons and neutrons. I subtract the two from one another. That gives me 1.1349 AMUs. I multiply that by 931 MeVs per AMU. This gives me 1,057. Let's see, I may have had a different, this may be, okay. What's the binding energy in joules? That's this problem. So I'm going to take the MeVs, multiply that by the conversion of joules to MeVs. This gives me 1.694 e to the minus 10 joules is my binding energy. Ladies and gentlemen, that is it. You are done with me, except for two little matters or a couple little matters of a quiz that's due this Sunday, a pop quiz that's due this Sunday as well, and two minor tests. Remember a couple things. The final will replace one of your test scores. Second thing, I'm just looking it up here. I thought somebody qualified. It looks like everybody is taking the final. So, ladies and gentlemen, I will see you on two more occasions. I will be here. I promise I will be in my house from class time, 10:15 to 12:30, actually 10 o'clock to 12:30. I believe I gave you 2.5 hours for the exam. I will be here during that time. You have my phone numbers. Honor Lock will be notified that you are allowed to call me. So if you run into problems, let me know. Look at your email before you take the test. Because if there's a problem with the test, this is the only way I can let you know.
Question about the final.
Yes.
Is it over everything?
Yep.
Or oh, that's fantastic. Okay.
Oh, I knew you
Other
were happy.
question?
I knew you'd be happy about that, Benita.
How many questions is the final?
I don't know.
Yeah, you do.
I don't know, Manuel.
Wait, so it's not 6 questions? Wait, what's 6 questions?
Right, because you said six questions.
I'm so confused.
Okay,
Wait,
I said 6
I'm-
questions. When did I say 6 questions?
It was maybe like last class or the class before that, but I remember 6
I
questions.
think it was the class before last one.
Okay.
Yeah, 6 is good.
What's on the screen, guys?
Nothing.
Good.
Nothing.
Thank you.
I have a question after that as well.
No problem.
Thank you.
Looking at quizzes. Final. One, 2, 3, 4, 5, 6, 7. I lied. There are 7 questions. One, 2, 3, 4, 5, 6, 7. Fair enough, guys?
Yes.
I have a question.
I'm sorry, Emmanuel had one before you.
Oh, it was just over the when you were multiplying the last like the last problem we did, and we had joules or
Okay, one
Over time.
second. I need to find the share screen again. Nuclear chemistry. Okay. This last
Okay.
step,
yeah, the 1.602.
that's
that
just
like
a conversion.
constant?
It's a conversion.
Oh, okay.
It's a
okay,
conversion of joules to MEVs. That's all.
Okay, gotcha.
Now, somebody else had a question.
I did.
Whose I did?
Jenna.
Yes, Jana?
Yeah. My question is, for the final exam, do those 7 questions include thinking questions as well? Or
No,
they-
they're all number problems.
All right.
The third test will contain thinking problems, though. Final does not. And think, ladies and gentlemen, think about what I emphasized. All right? Concentrate on those things that I emphasized. What problem specifically did I emphasize? These are rhetorical questions, guys. What did I emphasize specifically in kinetics, in intermolecular forces? What was a problem you all had extreme difficulty with? Colligative properties. Go through those. Learn for the equilibrium. Know how to do an equilibrium constant. And also know ice diagrams. Know ice diagrams forward and back. Know oh dear God, I've lost my mind. The buffer equation, Henderson-Hasselbalch. Know that. Know how to go from Gibbs free energy, how to get Gibbs free energy from Hess's law and by using entropy and enthalpy. Know how to know how to balance a redox equation. Know how to get the standard electron potential of a cell. Know how to get one from non-standard conditions. Know how to determine solubility products. Know how to know when you are precipitating a salt out. Know how to convert standard potentials to Gibbs free energy. Know how to convert it to a K. Know how to convert a concentration cell. Know the things we went over in nuclear chemistry, things we went over today. Going from time to how many nucleides are left, going from however many nucleides are left to the time. Know how to do half-lives, carbon dating, mass defects, and binding energy. Yep, it's a whole bunch. 7 problems.
I'm
Actually, you
assuming
should,
it's not multiple choice.
no multiple choice, none. Show your work. The more crap you throw at a wall, the more will stick. You never know what you're going to get points for. The more you put down, the more you have. I will not accept work emailed to me later on either test 3 or the final. You are going to have to type it into the text box. If you don't show work, you don't get credit. I will do my best to give you all the information you need and a periodic table. Anything else, ladies and gentlemen?
Professor, I had a question.
Yes, Araceli.
For the final, just like on the test, are we allowed to use our material or not for the final?
Yes,
Okay.
you are allowed to use anything except accessing another site. You're not allowed to access another site. This includes if you have the e-text. If that's it, ladies and gentlemen, I truly wish you good luck on the tests, and I really wish you good luck to you and your future. It's been a hard semester, guys. I know it has. I really wish you all the luck in the world.
All right. Thank you, Professor P.
Thank you.
Manuel, stay after.
Thank you.
Thank you.
You're all welcome.
Professor, can I talk to you after class real quick?
Sure, Leonardo.
Oh yeah, I just had a question really quick after class.
Okay. Is it personal
Like-
or not?
Kind
Yeah.
of.
Okay. Leonardo, is yours personal?
Not really. It's just about the test scores.
Yeah,
Test-
same actually.
Test scores for Leonardo, are we talking about? Okay,
Oh,
go
we're talking
for
about
it. I'm sorry, Leonardo.
because it says national test score for the first test was a 136 out of 150. That's above a
Okay.
90%. So
1 second, Leonardo.
Yeah, same.
Leonardo, I've got you at a first test as a 106. Leonardo?
Are you not counting the extra credit?
No. If you
God,
look at
there.
if you look at the syllabus. Oh, I'm sorry. Leonardo.
yeah.
Leonardo, I'm sorry. I apologize. The first test, because I had a resubmission, you're eligible to not go to the final, okay?
Okay, so if I get a 90 or above on the third test, then
If you get a 90 or above on the third test, what I will do is I will average the 3 tests, and that will be your final score.
okay.
Okay. Again, I apologize, Leonardo. I had forgotten that I had that resubmission. Okay, so you got 136 before the extra credit.
Okay.
So that qualifies you. Jenna?
Yeah, no, I think I got like a little below a 90 on the first quiz, and then the extra credit bumped me up. So I just wasn't sure if the extra credit was added, but I'm good now.
Yes. Yes, Jenna.
Gotcha.
If you look at the syllabus, it specifically states in there that you have to have 90% or better on the raw
Gotcha.
score. Okay.
No worries. Thank you.
Anything
for
else?
hosting.
You're welcome. Anybody else out there? By the way, you two, I'm sorry, I need to see something. Manuel, you still there?
Yeah, I'm here.
Araceli? Araceli?
Right here.
Okay. Is there any question? I'm done right now. Manuel, Jenna, and Leonardo, I'd like you to stay for a second. Araceli, do you need anything more?
No. So that's it. No more questions. Or
That's it.
I'm good. Well, thank you, Professor.
You take care, Araceli.
Take care. Thank you.
Okay. Let's see. Who else is, I've got Manuel and Jenna, right?
Mhm.
Yeah, it's just us three.
Yeah, I think it's just us.
And Leonardo. Okay, good. Basically.
Well, no, Leonardo is not here.
Okay,
Leonardo.
that's
Yeah,
fine.
Leonardo left.
That's fine. It's nothing major. I just wanted to say that this has been one of the hardest classes I've ever had to teach. I'm going to be perfectly honest with you. As a general rule, I'm sure you felt my frustration.
Mhm.
I'm sure you, let me do one thing. I'm sorry. I'm going to stop share for a second, and I'm going to stop